Okay, so let's get started. So let's start with a quick recap. In the last class, we started looking at an example vector space, which is the set of all n cross n matrices. And then on that, we introduced the notion of inner product. What was the inner product? Trace, right? And then we saw that this induces a norm called the Frobenius norm. So what is the Frobenius norm? What is the Frobenius norm? Hmm? Yes. What is the Frobenius norm? Hmm? What is the Frobenius norm? Yeah, what is that? So suppose I give you a matrix, how do you compute the Frobenius norm? Of course, one way is you take A transpose A and then take the trace of that square root, but uh, without that, so what is it that you'll be doing? No, you'll be squaring each entry, adding them and taking the square root, right? That's all you are doing. So that's what Frobenius norm is all about. Is that fine? Okay. So then we introduce to the notion of the orthogonality, right? So what do you mean by two vectors being orthogonal? Well, based on our intuition in R2, which is V transpose U is 0, right? So if you take the dot product, you should get 0, right? You will get 0 if they are orthogonal. Based on that, we generalized. We said instead of dot product, you take inner product. You say that if you take two vectors or 2 points from a vector space and take inner product, and if that inner product turned out to be 0, then we say that the two vectors are orthogonal, right? And then we saw this notion of how to get orthogonal vectors, right? Suppose I give you v1 v2, right? It need not be orthogonal. So how do you get the corresponding orthogonal vectors that span let's say v1 that's the span of which is equal to the span of v1 v2, right? So what did we do? What is that procedure called? It's called Gram-Schmidt's orthogonalization procedure, right? So we used Gram-Schmidt's, right? So of course, in the last class, I came up with so this method essentially gave us what is known as orthonormal. So there is another easier or straightforward way to come up with orthogonal, and then you can normalize it. Okay, so that's what we will see quickly. So and also there are other variants of finding these alphas or finding the orthogonal vectors. One can pose it as an optimization problem and so on. That is something that we looked at in the last class, right? So finally, we looked at QR decomposition. So we will revisit some of them. So first of all, let's look at, um, for example, let's look at the standard. So ortho, the notion called projection.